So we start a new chapter today. We're going to be spending quite a bit of time on functions, and this is kind of an introductory lesson on what a function is, how do we identify whether or not we do have a function or not. So let's just take this first example. This is number 15, as you can see on page 211. The directions for that block of problems there are for us to determine whether each relation represents a function. Well, a relation is a set of ordered pairs, but not every relation is a function. We need to remind ourselves what makes a relation a function. And if it is a function, we need to state the domain and range. Okay? Well, one way that you can identify a function from what we're seeing here, which is called a mapping diagram, is in general, you cannot have repeat values in the domain in order for this to be a function. And the way you would tell if you have repeats in the domain, which in this case would be the person square, is if you have an arrow, actually two arrows branching out from the same name. Okay? That would indicate that this person's name is actually used twice in the domain. So in general, if you have repeat values in the domain, then you cannot have a function. Well, in this particular case, that is not the case. I don't have two or more arrows branching out from any of these names. So therefore, this is a function. And now all we have to do is state, using set notation, what the domain is and what the range is. So pretty easy to do. The domain will be Elvis, Colleen, Kaylee, Marissa. And then the range will be their birthdays. January the 8th. Now, I do have a repeat in the range, but that is okay. I still have a function. I just cannot have a repeat in the domain. And if you have repeats, we really don't need to list them more than once. So January the 8th, March 15, September 17 represents the set called the range. All right, so one more time. If I had this situation, for example, Kaylee is being mapped not only to March 15th, but also to September 17th, which would make absolutely no sense. It means she has two different birthdays. Well, anytime you look at a mapping diagram like this and you see this scenario where two or more lines branch out from a domain, this cannot be a function. This indicates a repeat in the domain, which can't happen if it is a function. All right? So when we move to problem 19, the instructions change. You can just look there. Well, the instructions are the same, but the type of problem is a little bit different. Instead of a mapping diagram, we're just given a set of ordered pairs. That's what a relation is. So once again, if you want to decide if this is a function or not, look at the domain. That's the x coordinates. And see if you have any repeats. Apparently we do, because the number 2, if we were looking at a mapping diagram, would map to 6, and it would also map to 10. Well, this cannot be a function. And the way the directions read, it says for each function, state the domain and range. Well, this is a function, so therefore I don't need to state the domain and range. The answer would just be no. All right. Yeah, you're looking at the x coordinates. That's another way of saying the domain, and you're looking for repeats. Okay. Determine whether the equation defines y as a function of x. We are actually going to skip this section. So when you see, and I've eliminated it from your homework, so the block of problems from 27 to 38, you can just jump over those, and we're going to get to more exciting problems. So these are your instructions for the block of problems starting with number 39. From 39 to 46 in your book. You're not doing all of them, but this is the type of thing, and you can see this is a multi-part answer. It's one of the reasons why we're skipping that section above, because you're going to spend most of your time probably on these. All right, so what is this asking us to do? We're given a function in this number 39 problem, and we've got several different inputs that we need to take care of one at a time. So, yes. Okay, so remember what this notation stands for. This means I'm going to input 0 into this function, and I'm going to get the related output. All right, so let's just start off with letter A. F of 0 means literally, and you don't have to write this every time, but I just want to make sure you understand what's going on. I'm inputting 0 for x in this function. And when I do, the output becomes -4. So that would be my answer for letter A. Okay, using that same function, we'll do letter B. Let's input 1 in the function. F of 1 means I'm going to replace x with 1 in the function, and then see what comes out. So if you're not using a calculator, just remember the order of operations. You square first, and then you multiply. So this is 3. This would be negative or -2. So this should be -3. Yeah, it is. Thank you. Why did I put minus? 5 minus 4. Okay. Do you get the idea with numbers being plugged in? All right. What about, can we skip over letter C? You think you got that? What does this mean, letter D? Well, it means the same thing, except now instead of inputting a number, we're literally inputting -x in place of x. So everywhere I see -x, I'm going to put in, or x, I'm going to put in -x. A little jumpy. I think I'm going to move. Okay, well remember when you square -x, it becomes positive x squared, so this just becomes 3x squared. This is going to be subtracting, or you could add -2x. So that would be your answer for inputting -x. (3x squared). When you square -x, it becomes x squared. It's x squared. It's like -x times -x. What would that be? Got it? Positive x squared. Okay, any other questions? Everybody see how we got that? All right, I'm going to go to a new slide, and we'll take a look at letter E. This reads as the opposite of, or in other words, what if you multiplied the function by -1? Maybe I'll just squeeze that in up here. If I multiply this whole function by -1, which is really what that says, what does it become? -3x squared minus 2x plus 4. That's it. Yeah, literally that minus sign means what is the opposite of and you're basically just going through and changing all of the signs. All right, what about this? What if we input x plus 1 into the function? F of x plus 1. 3 times x plus 1 squared plus 2 times x plus 1 minus 4. Give myself a little space here since you already have this written down. So Micah, let's go ahead and square x plus 1. Okay, very good. And we'll come back in just a minute and distribute the 3. We'll go ahead and distribute the 2 here. And Adam, what is that? Okay, and then minus 4. So when you distribute the 3, 3x squared plus 6x plus 3 plus 2x plus 2 minus 4. So Gage, clean all this up for us. Give us a final answer. Combine like terms. All right, takes care of that. 6 plus 2x is 8x. Plus 1? Okay, sounds good. All right, any questions on part F? Well, if we need to, we can do the part G. That's just basically the same idea. We're going to input 2x in place of x. I definitely want to do this one because this is kind of giving you a sneak peek for those of you who are headed to either pre-calculus or calculus. You're going to learn about something called a derivative, and this is involved in that definition plus a lot more, but let's just go ahead and do this one because that'll be pretty important. I'm going to go to a new slide. Somebody read that function off to me when I go over. 3x squared minus 4. And we're doing f of x plus h. Okay, well, literally, wherever you see x, you're replacing it with x plus h. Okay, so Andrew, can you help me with squaring x plus h? No, it's got to have 3 terms. If you square a binomial, it's got to have 3 different terms. And we learned a little mental math process. You can multiply these together and then double it. What would that be? 2, we'll do hx, alphabetical. And then what's the last one? Square h. All right. And Kimber, we distribute here and we get good. All right, so Allie, distribute the 3. Okay, and we'll clean all this up. I'm going to go back to Adam. Let's combine like terms. Okay, takes care of that one. Okay, pretty long answer. Is it saying we didn't have any like terms? Okay. Good job. So you get the idea of inputting each one of these into the function and several different answers for these. I want you to work on number 42, all the parts, and then we're going to come back in just a minute and see what you got. Okay, so Andrew, what'd you get for f of 0? Negative 1/4. Very good. Who got that? Nice. Micah, what about f of 1? Okay, which is just 0. Who got that? Very good. We're 2 for 2. Kimber, what about f of negative 1? Also 0. Who got it? We are 3 for 3. All right. Adam, what'd you get for letter D? Okay. See if I can squeeze that in. Who got it right? Who has a question about that? If you input negative x in place of x, which is what it says to do, it becomes x squared. And down here it just becomes negative x.
If you square negative x, it's just x.
I'm not sure how you're getting that. That's like saying if I square negative 2, I should get 2. I mean, okay, so in other words, let's put a real number in here. What is the answer to that? So what did we do? We just multiplied the number times itself. Sure. 5 equals 5. 10 equals 10. Okay, so are we good now? Let's go down to the opposite of f of x, and let's see. Micah, haven't called on you yet. Have I? Okay, I'll call on you again. Let's put it back the way it was. Give it a shot. You're among friends. So basically what we're doing is this. Actually, if you just left it like that, it'd be okay. Well, one of these would have to change. It really doesn't matter which. We got to show a negative fraction. So you could either, instead of putting the minus in front, you could have changed the numerator signs. So you could have shown it like this. If you change both, then you've done a positive. Negative divided by negative is positive. You just put it back the way it was. To make a negative overall fraction, you just need to change either. What do you mean? Okay, question. Okay, I'm going to pause this. All right, so for letter E, once again, just to finalize this, in case I didn't record this earlier, you can change the whole fraction with the minus sign. You could change just the numerator, or you could change just the denominator. Any one of those three would be okay. Okay. All right, so let's pick up with F on this slide. And I'm just going to work through this one, see if we'll get it right. So we're going to replace x plus 1 in place of x in this function. Okay, x plus 1 quantity squared minus 1, x plus 1 plus 4. So the numerator, when we square this, becomes x squared plus 2x plus 1, but then we're going to subtract 1, x squared plus 2x. Okay, who got that part right? Does it make sense? Just tell me what you did. Or Adam, go ahead, and then we'll go. Okay, we need to talk about that. All right, let me go ahead and finish this thought. And on the bottom, you end up with x plus 5. Okay. We need to make sure we understand why what Adam said isn't good. Sorry, pick on you, but I'm glad you said it. Here's the deal. We have two terms. This is called a binomial. Two terms. The bottom has a binomial. Two terms. All right. You can always cancel factors, but you cannot cancel individual terms. Okay? Let's prove it. It's always good to use some actual numbers. Let's see if I can make this come out into nice. Let's do this. What's the answer to this? Simple little 5? Okay. Well, doing what you said, I should be able to do this and get, well, we've already said that can't be the answer, but this kind of proves to you why you can't cancel terms, but you can cancel factors. Okay. Yep. Okay, what did you do?
Since x plus 1 is squared, it would just make x plus 1 times x plus 1.
Which is x squared plus 2x plus 1.
Yeah, but I didn't do that. I just canceled the x plus 1 from the bottom. So I just got x plus 1 minus 1.
Yeah, and the problem with that is you've got to complete this denominator before you cancel. That's really not, again, that's not a factor. Remember what's the difference between a factor and a term? Well, a factor is something being multiplied. That's a factor. What you have is really just another term. Big difference. Now, if it was written like this in the denominator, I would agree you could have canceled the x plus 1s because you've got factors. Right. Now does it make sense? So who got this right? Missed it? Oh, you got it right? Do you see why?
Yes.
Okay. All right, let's move on to G. We're getting near the end. So f of 2x means we're going to put 2x in, square it, minus 1, 2x plus 4. So in our numerator, we should get 4x squared minus 1 over 2x plus 4. Done? Anybody stop there? Could we maybe simplify this? Well, you're partially right. Can we factor this? Difference between two squares? Allie, what's that look like in factored form in the numerator? Two perfect squares being subtracted. I'll get you set up. What are the square roots of each? How's the bottom factor? Micah? Oh. Now we're done. So I want you to train yourself when factoring is possible, because without factoring, we don't know if we can simplify. And you're going to miss opportunities to simplify if you don't factor. That makes sense? So you need to recognize when factoring is possible and when it's not. Okay, we're almost done. Let's do the... Sure. Let's input x plus h into our function. So x plus h squared. I don't know what's wrong with that spot, but it doesn't work well. X plus h squared minus 1 over x plus h plus 4. All right, real fast. What's this squared gauge?
No, x squared plus 2xh plus h squared.
All right, good. Over x plus h plus 4. And nothing can be simplified from that point, no like terms, so we're good. Okay, almost done. This is the last part of your assignment. They're going to give you functions. It's your job to identify the domain. So when we say the word domain, give me another letter that we associate with domain. X. Okay. What's another word that we associate with domain? Input. Good answer. Okay. So here's the goal of this block of problems. When you're asked to identify the domain of a function, what they're really wanting to know is what numbers are allowed, or you might think of it as the opposite, what numbers are not allowed to be inputs. So here's the big deal. When you have a function, we always have to avoid this. Is that even possible?
No. It's not even possible.
We can't divide by 0, so we've always got to keep that in mind when we think about inputs. We've got to avoid division by 0, and we also have to avoid this. We can't do the square root of a negative number because that's not real, and we're only dealing in the real number system. All right, so for number 49, I've got to avoid division by 0 when I put a number in for x. Well, am I going to have to worry about 0 in this denominator? I mean, let's think of a number that we could plug in to this denominator and make 0. There is no number. And if you want to prove it to yourself, go ahead and solve this, and if you end up with I involved, then that means it's not possible to make this 0. There is no number. So for this answer, we're just going to say all real numbers. We don't have to worry about division by 0 because it's not possible. Now 51, a little different story. And once again, I would recommend that you factor when you can. Now we've got the potential of division by 0 if x is one of two different numbers. All right, so we're going to state the domain as this. Instead of saying all the numbers that it can be, we're just going to say x cannot be positive 4 or negative 4. It can be any other number besides that. Okay, well what about this one? What are we trying to avoid here? We can't have a negative under the radical. So in other words, what about 0? Is 0 okay? Can we do the square root of 0? That's 0. But we just can't have a number less than 0. So let's see. Let's let this be an inequality. Well, let's see. I mean, what we're saying is x might be a negative, but this whole expression cannot be a negative. That's the point. Okay? Well, let's see. If we let this be less than 0 and solve, what do we come up with? 3x. 3x is less than 12? Okay, so what we're saying then, if If we have 4, it's okay, because that would make the square root of 0. But if I have 3, then I'm going to have 9 minus 12, which is negative 3, and I'm going to have the square root of a negative number, which isn't okay. All right? So, in other words, I can let my domain be any number that's 4 and above. So we could say it like this. As long as x is greater than or equal to 4. We've just proven that numbers less than 4 are going to create a negative under the radical. Okay, what are we trying to avoid on 61? Really 2 things. Okay, so let's start with the denominator. What would make this denominator 0? Well, if you're not sure, set it equal to 0 and solve it. So we definitely cannot let t be 7 because that creates 0 in the denominator. So that's off limits. What about for the radical? Can t be 4? Yes. Can t be 3? So how are we going to express it? T can be greater than or equal to 4. As long as we don't create a negative number under the radical, we're okay. So we're going to say t can be greater than or equal to 4, and but it can't be 7 because that causes problems with the denominator. Okay, any questions? I'm going to just, since I'm almost out of time, I'm going to eliminate that last part, and we'll talk about that on Monday. So that basically removes this one.